Okay, good morning, everyone, and thanks for joining us for this presentation on the HS1760 Switched Fabric. Let's get started. So this is going to be a tutorial on the HS1760 Fibre Channel Avionics Environment Switched Fabric. We'll cover several topics, but the main objective is for those who are new to HS1760 protocol. The goal is to help you understand the terminology, the characteristics of fiber channel networks, and especially regarding how avionics environments differ from standard fiber channel networks. This is the third and final presentation of a multi-part webinar series from AIT regarding the HS1760 protocol. So if you'd like to check out the earlier presentations, recordings of them are available on AIT's YouTube channel. Okay, so HS1760 is the common name for the MIL standard 1760 high-speed option. We've already covered some basics of this protocol in the first and second webinars in this series. In the first webinar, we provided an overview of the protocol for HS1760. And the second webinar dove into the Fibre Channel FCAE 1553 protocol, which is the MIL standard 1553 protocol mapped onto Fibre Channel. MIL standard 1760 chose the SAE AS5653 protocol as the high-speed communication standard, and then that standard defines the use of FCAE 1553. Fibre Channel is a switched network protocol. This was initially designed for commercial environments. The initial design-in of Fibre Channel was storage area networking, and really it was to replace old SCSI systems. Fibre Channel was competitive in its early years for local and wide area network integrations, but was pretty quickly edged out by Ethernet. And you can still find new installations of Fibre Channel in storage. Fibre Channel is very highly valued by the SAN community for its reliability and its determinism, especially when you compare it against Ethernet, the primary competitor. A unique feature of Fibre Channel is the early implementers understood its value in avionics environments, which is why a number of AE protocols or avionics environment protocols were created. There are references to the avionics environments in the FC-SW4 standard, which is the governing standard for Fibre Channel switch fabric. And the AS5653 profile of Fibre Channel refers to some of those AE features. So today we'll take a detailed look at that FC-SW standard with the goal of understanding the fundamental terminology, the topology of the switch fabric, and what major differences from commercial to avionics environments there are. So in other words, if you're interested in finding a Fibre Channel network switch for an AS5653 network, my hope would be that after this presentation, you'll understand which products you should be looking for and why. Okay, so Fibre Channel defines a number of different topologies. That would include point-to-point, loop, and switched fabric topologies. If we consider the example here pictured, we have a switch fabric topology where there are two network switches. Connected to the switches, we have several different nodes. For those listening who don't speak network lingo, a node would just be the formal name for any kind of computer that's connected to the network and either produces or consumes data from that network. There can be different types of nodes connected to the network. So in this case, you can imagine different LRUs on an avionics network. And since I only have images of AIT devices, I've shamelessly plugged some of those into the diagram here. So those are the orange boxes. But they could represent different LRUs, such as navigation computers, mission computers, other types of avionics devices, right? But at the end of the day, in terms of the network, we can just refer to those as nodes. And I should note that fabric is the term for a star topology network where devices can pass data through any path in the network. The paths of communication can be overlapping in all kinds of different ways. And so if you picture those overlapping communication paths, it kind of resembles fabric. And so that's where the term fabric came from. And Fibre Channel uses that term fabric to describe the various links and the switches necessary to connect all the nodes together. The Fibre Channel terminology for a port on a node is an N port. So N port just stands for node port. And a network of just two nodes and no switches, both nodes would normally be N ports. Also, in a fabric environment, each node will connect to a switch using an N port. Nodes can have multiple ports connected to the same fabric for redundancy or additional bandwidth. In this situation pictured, nodes will generally log into the switch fabric to receive their address, but it's also possible to implicitly log on to the network. An implicit login would be when the node knows what its port address is going to be without actually going through the process of logging in. Most avionics networks do use implicit login with a pre-programmed port configuration in order to reduce latency, especially between power disruptions, but also just to get up into an operational state. For the port on the fabric side of each N port, there's going to be an F port, where F port stands for fabric port. And fabric ports actually start as a G port, where G stands for generic, so generic port. G ports could also be GL ports, where a GL refers to a generic loop capable port. So Fibre Channel has the ability to do a loop or a ring network, and it would be referred to in Fibre Channel as an arbitrated loop. And if you're well versed in Ethernet lingo, that would be really similar to like a token ring environment. Arbitrated loops can connect to the fabric through a switch GL port. Also, the nodes in an arbitrated loop would be NL ports or node loop ports. With any node port that connects to a switch port, the switch will determine what kind of port it has connected to it and then resolve from the GL port or G port to an F port or an FL port. There's another case also where the switch will have one or more expansion ports. An expansion port, or just E port, are the special switch ports that are capable of inter-switch links that expand the fabric beyond just one switch. In this case, the two ports that connect the two switches together are referred to as E ports. This illustration is taken directly from FC-SW-4. In this example, all possible configurations of ports are demonstrated. The cloud shape represents the fabric, and the circular diagrams within the fabric represent network switches. The boxes represent different types of ports. Within the fabric, if a port connects to another switch, it is labeled E for E port. If it is N, then it is an N port. You can also see the example of an arbitrated loop at the bottom, where the NL ports connected in a loop are connected to the FL port of the switch, effectively integrating the loop into the star topology fabric. If we take a look at this loop network at the bottom, each port on the loop is responsible to pass along data that isn't addressed to itself. So if any of the ports go offline or have any kind of failure, then many of the devices on the loop are now incapable of communicating. Loops in a Fibre Channel network are prohibited from HS5653 environments on account of their inability to handle disconnections within the loop. FC-SW-4 defines a number of important services. There are also additional services defined in the Link Services Standard FC-LS. One important one for avionics would be the clock sync server service. That's out of scope for this conversation, but certainly interesting for avionics. The table here describes at a very high level some of the important services of the Fibre Channel fabric. This is not a complete list, and some of the services are clumped together in one row. The goal here is just to provide a high-level overview of those services provided by the network. Those include E-port and F-port operation. As already mentioned, E-ports or expansion ports are for making inter-switch links. So these ports expand the fabric. F-ports provide services through what are known as well-known addresses. For example, to log into a switch, an N port can send a message to a well-known address, and the F port will provide the N port a network address. Another service provided is path selection through a protocol known as FSPF, or Fabric Shortest Path First protocol. There can be multiple paths through a network, and those paths could be used for load balancing or redundancy or other purposes. FSPF, Fabric Shortest Path First protocol, is the method used for finding the correct path through the network. There are a number of server functions that are implemented in a distributed fashion on fiber channel networks. That being the case, each switch is responsible for certain network functions. For example, network services such as broadcast or multicast, port address assignment, name translation, and other functions of a network server are distributed amongst the switches. The Fibre Channel Fabric also provides a system for event notifications between switches, which is important for managing some of the distributed server functions. The switches must also support a service for the exchange of information between switches to support zoning. Zones are like Ethernet VLANs and are used to isolate traffic within certain portions of the network. There's also a protocol for virtual fabrics where you can actually define separate portions of switches to behave as a virtual switch. When you initialize a fiber channel fabric, the first step is determining the principal switch. The principal switch is responsible for address management algorithms and basically becomes the domain address manager. Each switch that is not the principal switch will request their respective domain IDs from the principal switch. Principal switches, once elected, resolve each path as either an uplink or a downlink. The principal switch has no uplinks by definition. So any path toward the principal switch is just referred to as an uplink, and any path away from it would be referred to as a downlink. So if we just turn now to the avionics environment, there are some additional things that we have to define. In an AE network, switches implement AE services to make a switch what we call AE capable. So AE capable switches must have at least one AE capable port. AE capable switches must also implement the protocol defined in FC-SW4 Annex D, known as Fast Fabric Initialization, or just FFI. The FFI Annex in FC-SW4 identifies a few really important assumptions to be norms within avionics environments. And so first, in the past, network environments on aircraft were fairly simple, typically just point-to-point systems or maybe just one switch. But the expectation is that in the future, or likely really now, the switching environment generally employs more than one, and it could be many switches. Commercial systems don't typically have real-time constraints, but obviously avionics environments do. So the standard defines some objectives for avionics fabric deployments, and those are listed here: determinism, low latency, predictability, reliability, and fault tolerance. The standard also notes that an avionics system is going to differ from commercial ones in topology, in that avionics systems are typically static, and so you're not going to have changes to the interswitch links or domain maps in the middle of a mission. Like once you're powered up, you don't need to redefine the network from moment to moment. Whereas in a commercial environment, everything's typically plug and play, and they're going to use self-discovery protocols. So they can power up and, not knowing anything about the network, define the entire network. But avionics systems are totally static, well-known, fixed configurations. And those plug and play protocols are fairly sophisticated, and they generally add unnecessary overhead to an avionics environment fabric. So for the AE fabric, we're just going to eliminate those protocols. Without self-discovery, our AE fabric will be more predictable, it'll be more reliable, and it can reduce the latency from any kind of power interruptions to the active state. Fast fabric initialization is a modified version of the switch initialization protocols defined in FCSW4. Annex D defines the FFI protocols. FFI provides a method for defining an implicit network, eliminating the principal switch selection and FSPF. Replacing those eliminated protocols is a static configuration environment. An AE principal switch is defined by predetermined configuration, which is stored in the switch. As with the standard principal switch election, the AE principal switch is the only switch in the fabric with no uplinks. Downlinks are defined as interswitch links that lead to an active AE port and that contain no paths to the AE principal switch. Uplinks are defined as interswitch links toward an active AE port where at least one path leads to the principal switch. After init, there's going to be an unambiguous domain topology map that defines the entire network. Specifically included in that map are all of the domain IDs and interswitch links of the avionics fabric. The map is managed and held by the AE principal switch, and the map is distributed to all other switches by the principal switch. A secondary AE principal switch can be defined, but the two switches may not be active as the principal switch simultaneously. The secondary AE principal switch identifies itself by setting a flag in the response to the AE principal switch during init, and then there's a handoff protocol established to pass principal switch behavior to the secondary switch. Normal fiber channel switches do not require config files. They can initialize a complete network without knowing anything about the network in advance. But in an AE network, since the network map is defined in configuration, the AE switch needs to be capable of configuring from static pre-programmed config files. So I've just got one more topic to cover, and that is the AS5653 starting at Rev B, addressing this common situation in avionics environments where data prioritization is helpful. It's possible that AS5653 will carry high bandwidth applications. In a normal fiber channel network, the link level provides what we call buffer to buffer flow control to throttle network traffic to the highest possible data rate for all messages without dropping any data. This flow control mechanism uses a simple link credit referred to as the R-ready or receiver ready signal to increment buffer credit for the transmitter on the other side of the link. When the transmitter runs out of credit, it just stops transmitting. It doesn't send any additional traffic until it receives another credit. This very simple protocol ensures that no frames are dropped as a result of buffer overflows. The flow control mechanism works independently for every link in the network. In a typical high bandwidth application, there's generally going to be a producer of the high bandwidth traffic and then a consumer or multiple consumers of its data. It's possible, it's likely even, that each link in the path from the producer to the consumer or consumers will become saturated. Each buffer is going to, in the switch ports and the node ports, are going to be filled, and they're just waiting for some system driver to handle their incoming data. In that case, if there is a high priority, low bandwidth signal that needs to use the same links and buffers, it's going to be impeded, and obviously that's going to just increase the network latency for that high priority data. So in AS5653, an additional high priority mechanism that can bypass the standard buffer credit system is made available. AS5653 takes advantage of the fact that recent versions of the fiber channel standards have effectively eliminated what used to be referred to as class 4 features. They were just never implemented, and so that class 4 traffic had been planned to use a link credit mechanism that was referred to as the VC ready or virtual circuit ready token. This was fully defined in the standards, but just again, it was just never used. So AS5653 repurposes that link credit mechanism as the buffer-to-buffer flow control mechanism for high priority traffic. The standard requires that a compliant switch, an AE compliant switch, will provide separate buffers for low and high priority traffic. So in the switch model shown here, which again is lifted straight from the FC-SW spec, we would just need to clarify how the switch port buffer model works. In the standard switch model, each port will typically have at least 2 buffers, sometimes 3 or 4. And that buffer count or credit is identified during initialization for each port. This diagram represents a switch with 2 buffers per port. When the link's initialized, the credit count, again, it would just be identified as 2. But in the AS5653 model, it's assumed that if the initialization process declares that there are 2 buffers, then this means that there are 2 low priority and 2 high priority buffers. So if a switch in the network does not understand the modified high priority mechanism, it's actually still going to work based on the way this is all designed, but it will impede high priority traffic. Okay, so to recap, there's a couple of really important differences in HS1760 network standards versus their commercial counterparts. The first major difference is that the network is going to be configured from stored files rather than plug-and-play discovery protocols. So you'll need to find switches that can initialize from those stored configs. The next major difference is that the switches need to support FFI. That's the Fast Fabric Initialization Protocol for establishing the principal switch and transferring the domain topology map. And then the final major difference is that AS5653 Rev B defines a high priority mechanism, and it's important to find devices that understand those modified protocols so that they don't impede high priority traffic. AIT produces a number of tools that meet these requirements. I've got 2 of those pictured here. These are 2 variants of switches that we've built. The one on the left is a ruggedized switch for an HS1760 environment with a built-in FCAE1553 network controller. Again, we talked about FCAE1553 and network controllers in one of the earlier presentations in this series. And the device on the right is a simple 16-port desktop switch that supports AS5653 protocols, including FFI and high priority flow control. Finally, I'll just mention that we also have lab and flight versions of HS1760 network interface cards supporting FCAE1553 network controllers and network terminals. Thanks for joining. I appreciate your time, and I really look forward to working with you on your next FCAE1553, HS1760, or AS5653 networks.